All right, so we're doing probability of one event and another event. And so we're going to find the probabilities of independent and dependent events a little bit today. So the probability of independent events, if A and B are independent events, meaning one does not affect the other, then the probability of A and B occurring is the probability of A times the probability of B. So these are mutually exclusive. They don't have anything from one that affects the other. So we'll do some that are like that and some where they do affect. So the first question that we have, I'll try to focus this a little better, says, what is the probability of flipping heads on a coin 3 times in a row? Okay, so a coin has tails and heads. So the probability the first time of getting heads would be 1/2. And the second time it's still 1/2. So the first flip doesn't affect the second flip. And the third time it's still 1/2. So you have 1 times 1 times 1 is 1. 2 times 2 is 4 times 2 is 8. You could also figure this out by drawing a really elaborate tree diagram, which I think some of you have told me you did in middle school. But this is just a fast way to do it. It's just the probability of each one and multiplying them together. All right, so let's take a look at our next couple of examples. So it says a die is rolled twice. What's the probability of rolling a 2 and then rolling an even number? So these are 2 separate rolls. So first of all, what's the probability of rolling a 2? 1/6. Good. What's the probability of getting an even number?
1/2.
1/2, or you could do 3/6, but you could just go, okay, half the numbers are even, so you could go ahead and reduce that. And so then if we multiply, we get
1/12.
1/12. So if you weren't thinking 1/2, you could have also done 1/6, and then there's 3 even numbers. You could have done 3/6, got 3/36, and it would still reduce to 1/12. So no harm done if you did it that way. Same thing. All right, so on the next example, it says 2 cards are randomly selected from a standard deck of 52 cards with replacement. That's important. They're putting the cards back. So you could, in theory, draw the same card twice. What is the probability that you drew a king and then a heart? So how many kings are there? 4 out of 52. And then you're putting that one back. And then how many hearts are there? 13. So there's 13 in each suit. So then you could multiply those out. Or you could do a little bit of reducing. 4 over 52 is actually 1/13. And I could go, oh, look, this 13 and that 13 cross off. I end up with 1 over 52 without multiplying big numbers and then having to reduce them. I don't like reducing large fractions, so I like to do it that way. You could also take 4 times 13. You'd get 52 over 2,704, but then you have to reduce that. So if you'd taken the 4 times 13, you would have gotten 52. If you multiplied the 52s together, you would have gotten this, and then it reduces back to 1 over 52 in the end. So I just reduced it before I multiplied, which makes it a little easier. Okay, so let's look at the next problem. In a survey, 8 out of 13 children responded yes, and 6 out of 15 adults responded no. We have no idea what the survey was. We just know that 8 out of 13 children responded yes, 6 out of 15 adults responded no. If the next 3 people who responded to the survey were 2 adults and 1 child, what is the probability that they all responded yes? So we're using the previous results to do this. So we have 2 adults. Okay, so the probability that they all responded yes. Okay, so 6 out of 15 adults responded no. So how many responded yes? 9. So 15 minus 6 is 9. So there's 9 adults that said yes out of a total of 15. And then you're going to do another adult, and we're still going to say that that's about 9/15. And then we had 8 out of 13 children responding yes, and so we can set that up this way. Me personally, I would reduce these fractions first because that's going to make this easier. So 9 and 15 both reduced by 3, so I can change that to 3/5 and 3/5. And then when I multiply, I will know that I don't have to reduce anything else. So 3 times 3 is 9 times 8 is 72. 5 times 5 is 25 times 13 is 325, is that right? Anybody want to check me on that? I realized I had a mistake in last year's notes, so I'm trying to fix it or make sure. Oh, I have a calculator right here.
Yeah, 325.
325. And if we reduce everything on the front end, we shouldn't have to reduce anything on the back end. Okay. There we go. All right. Hopefully I didn't make any mistakes there. If the next 3 people who answer the survey are children, what is the probability that at least one of them answers no? All right, so we know that,
5 answers.
so yeah, we know that 8 out of 13 responded yes. So how many responded
5
no?
out of 5.
5 out of 13. So 5 out of 13. Trying to decide if we can actually do it that way because we want at least one of them answering no. So what we ought to do is think about this in terms of the complement. So the probability of getting them to say yes, let's do that first, would be 8 out of 13, 8 out of 13, and 8 out of 13, which comes out 1685 over 2197. And I'm going to use a little space below. So the probability of them not saying yes, of them saying no, is 100%, which is just 1 minus that number. I don't think this comes out the same as multiplying the 5, so we can check it here in a minute to see. This is what I have in my notes. Oh wait, this is wrong. 8 times 8 times 8. Hang on. 8 to the third is 512. There we go.
Yeah.
And then 13 to the third is 2197. Okay. And so then if I take and subtract that number from 1, I'm just going to do it on my calculator really quick. And, oh, except 1 minus 512 divided by 20. So this is what I typed in. And I got this weird thing, and then you can hit the math key and choose number 1, and that'll change it back to a fraction. And this is the answer that we want. So just out of curiosity, let's see. So let's do 5 times 5 times 5 is 125. Yeah, it doesn't come out the same if you just do 5 and 5 and 5. So we did have to subtract it from the 1. I had to think about it. Right.
Can we skip
So, no. All right, so let's go on to the next problem. All right, you spin the spinner 3 times. What's the probability of spinning a 4, a 3, and then a 1? So you notice some of the numbers do repeat. So the probability of spinning a 4, there is 1 4 out of 8 things, so that's 1/8. Of getting a 3, there's actually a couple of 3s, so that's 2/8. And then getting a 1, there are 3 1s, so that's 3/8. And if you want to, you can reduce the 2/8 right here and make it 1/4. That makes the multiplication easier. We end up with 3 out of 256. So it goes pretty quickly. Alrighty. I'm going to skip the next problem, so you can cross that off. I didn't have that one in my notes from last year, and I think there was a reason for that. It had a typo. So I'm going to go ahead and skip down to here. So they're going to give us some just very generic problems. It says events A and B are independent, meaning event A does not affect event B. So this is similar to one that we did in the last lesson. So the probability of A happening is 0.4, which is 40%. Probability of B happening is 0.5, or 50%. So probability of A and B happening, you would just take 0.4 times 0.5, 40% of 50%, and you end up with 0.2 or 20%, if that's how you want to think about it. And then there's a problem where they leave us a blank. They tell us that the probability of A is 0.7. B, we don't know, so I'm going to call that X. And the probability of A and B happening is 0.2.
0.7 divided by.
So yeah, you could think of it as an equation, or you could just divide them. 0.7 divided by 0.2. Oh, actually, I did that wrong. Got to do that the other way. 0.2 divided by 0.7. And we get roughly, and so if you just were like change that to a fraction, you could move the decimals over and get 2/7, which is approximately 0.3 is what I have written down. It comes out like 0.29-ish. Since these were in decimals, I like having the answer in decimals. Or it comes out 0.285, I guess, but that rounds off to 0.3. So we'll leave it there. Do our significant digits. All right, so on the next page, we're half done. It says a bag consists of 3 red, 4 white, and 2 blue marbles. So you can kind of see they're labeled. These are the reds, the whites, and the blues.
But it's not like it says 3 reds and no
It says find the
Oh, it says 3 reds, and there's only 2 reds. Okay, so let's change it to 2 up here, just so we can keep the picture. Sorry. So 2 red, 4 white, and 2 blue. There's a typo either here or there. I'm not sure. Find the probability of the following if the marbles are not replaced after each draw. So this would mean that they are dependent on each other. So I'm going to write that word, dependent. So the first draw, or the second draw will depend on the first draw, and so on and so forth. So we're going to do number 1, the probability of getting a red and a red. So my first time of getting a red would be 2 out of 1, 2, 3, 4, 5, 6, 7, 8. And then if I don't replace it, that means I took this red away, then there would only be 1 red left and 7 marbles left. Does that make sense?
Yeah.
And if you want, you can reduce the 2/8 off the bat and make that 1/4. So you have 1 times 1 is 1, and 4 times 8 is 28. Or you can multiply them and then reduce. Either way works. It doesn't matter. Then let's do the probability of doing a, I'm just going to use a W for white, a W, and then a blue, and then a blue. Okay? So white and a blue and a blue. So I'm going to take this off. Okay. So the probability of getting a white, there are 4 whites in the bag, is 4 out of 8. And then if I'm not replacing that, so I took out a white, I still have 2 blues down there, but now I only have 7 marbles. And then if I took that blue out and did another blue, now there's only 1 blue left and 6 marbles. Does that make sense? And so if you want, you can reduce the 4/8 right off the bat, make that 1/2. And then, and then this 2 and this 2 can cancel. I'm just going to cancel all kinds of things. And we end up with 1/7 times 6, which is 42. Or if you prefer, you could get 8/336 and reduce it from there. But I like to reduce it on the front end, not on the back end, because the numbers are so much easier. Okay, so, and somehow these questions didn't print off, so, and it didn't happen last year either, so I've got it written out. Okay, let's look at the next one. A bag consists.
Why are these all wrong?
I think it's because this was a PowerPoint and it was animated and it was actually taking the marbles out of the bag when I printed it. So it's okay. We're gonna fix it.
Yeah.
So a bag consists of 3 red, which we have, 4 white. I'm just gonna add a white to the bag. And then 2 blue. So I'm going to add a blue in there and I'll shade it so it kind of looks. So we're just going to add a white and a blue to the bag so that it matches what it actually says up here. Find the probability of the following if the marbles are not replaced after each draw, meaning that one draw is dependent on the draw before. These are dependent. Okay, so first we're going to do the probability of a red and a red. So there are 3 reds in the bag, and there are 9 total marbles this time. And then if I take that red out and don't replace it, how many reds are left? 2 out of 8. You guys are so smart. Okay, and so we can reduce these over here. So 3/9 is actually 1/3. 2/8 is actually 1/4. And we end up with 1/12. And then I'll get rid of my little X here. And so the next one we're going to do is the probability of a white and a white and a blue. Okay, so the first white, what would the probability be? 4 out of 9. I heard somebody back there say it quietly. So we took a white out. White out.
Yeah.
Okay.
Wait, so why exactly do we do red by itself and then...
Yeah, why did we mix white and light blue?
Just because that's what I picked.
Okay.
Oh, you can choose.
So we took a white out, and now there's only 3 whites left and 8 marbles, and we'll cross off the second white. And then we're going to do a blue. So there's still 2 blues, but there's only 7 marbles. Okay, so there's no fractions you can reduce, but we can reduce across fractions. So the 4 over here with the 8 over here we can cancel and make that 1/2. This 3 with the 9 becomes 1/3. And then this 2 with that 2. You can just kind of keep canceling. Makes those 1. So I have 1 times 1 times 1 now. And 3 times 1 times 7, which is 21. Alrighty.
Very simple. I always get like this.
So the next couple of problems, the next one is nothing like the others, so no. Sorry, they're here for a reason. Alright, so a survey showed that 58% of middle school students went to the beach during the summer. Of those who went to the beach, 34 of them also went on vacation. Of those who did not go to the beach, 77% of them went on vacation. What is the probability that a randomly select student did not go on vacation? I'm going to show you guys a nice little graphical way to do this, but you're going to have to write small. Okay, so we're going to start with the total students, which we actually have no idea how many total students there are, but that's where we're going to start, is with the total. And then we're going to branch this off, okay? And so there were 58% that went to the beach. So I'm going to put beach, and I'm going to change 58% to 0.58, okay? So 58% of them went to the beach. Then how many did not go to the beach? They don't tell us that. We have to figure that out. So 100% minus 58 would be 42%, or 0.42. I'm going to use decimals because that's what we're going to have to do when we get to the end anyway, so I'll go ahead and convert them. So they tell us of those who went to the beach, 34% of them also went on vacation. So of this, I'm going to say vacay, because I don't feel like writing vacation. 34% did that, which means that 66% had no vacay. I thought about putting vaca, but then that's cows, so it'd be like cows and no cows, so I didn't do that. So I'm just kind of doing some subtraction to figure out all these different pieces. And then of those who did not go to the beach, 77% went on vacation. So vacay, 77%, 0.77. And then you can subtract the 77% from 100%, or 0.77 from 1, and find out the ones who did not go to the beach that also had no vacation, poor people, no vacay, would then be 23%. So I just like to get this all straight in my head before I answer questions. All right, so if I go back to what it's actually asking, it says, what is the probability that a randomly selected student did not go on vacation? All right, so we have some here, and we have some here, and we can't just add those together. Okay, so there's 58% of the total, and then 66% of those. So this part right here, these people that did not do vacation, you have to take 0.58 times 0.66, because they're 58%, and then out of those, it was 66%. And then we're going to add those to the people over here who didn't go to the beach, who also had no vacation. So you have to do the 42% and the 23%. And this is a nice calculator problem that comes out 0.4794, which is roughly 48%. If we're keeping the same number of significant digits that were in the original problem.
So Miss Homer, the way you just did this or whatever is the same way they do it on statistics, but now it actually makes sense because someone explained what
Okay, so this diagram, since they're asking about the people that didn't go on vacation, they didn't give you those numbers. So this diagram kind of helps you figure it out. Okay? So these are really involved, but really it's just multiplication and addition once you sort out who's where. Okay. So we're almost done. What is the probability of drawing an ace and then a king from a standard 52 card deck without replacement? So we're not putting them back. So first, how many aces are there?
4.
So that's 4 out of 52. And then you're not replacing, and we want to get a king. So there's still 4 kings in there, right? But there's only 51 left. Now 4 and 52 actually will reduce to 1/13. So I like to do that. I don't know if anything else reduces. You end up getting 4 out of 663. And if we wanted to, we can convert that to a decimal and a fraction, a decimal and a percent. But for this, it's easier just to leave it as the fraction. All right, what is the probability of drawing a face card and then a 7 from a standard 42 deck card? So face cards, I think, are just the jacks, kings, and queens. In some games, sometimes they count the aces sort of the same, but we're just going to say the ones that actually have faces on them. So you would have 3 of them for hearts, 3 for diamonds, 3 for clubs, and 3 for spades. So that would be 12 face cards out of 52. And then you're going to pick a 7. So there's 4 7s, and there's only 51 cards left. And so there's ways to reduce this.
3/13.
So yeah, so 4 goes into 52 13 times. And then 12 and 51 both divide by 3. This would be 4, and this would be... my mind just went blank. I know it divides by 3. It's 17. Okay, and so that just made it a little easier, and we end up with 4 221. You could just multiply it and then reduce it afterwards, but you get some pretty big numbers, like in the thousands. So it's better to reduce it on the front end than on the back end. Okay, the last problem is just a nice generic problem. It says A and B are dependent, meaning that the first one affects the second one. So it has the probability of A is 0.1. And then this right here is some strange notation we haven't really encountered yet. This means the probability of B after A has already happened. So they've already done that subtraction for you. So if you're going to do probability of A and B, it's still 0.1 times 0.6, and you get 0.06, or about 6%. Or not about, it is 6%. And so then down here they have the probability of A is 0.91, and the probability of A given that, or B given that A has already happened, we don't know, so we're going to call that X. And then the probability that they both happened is 0.53, so we just have to divide 0.53 by 0.91, and we get roughly, if we're keeping the same number of significant digits, 0.58. All right, we're done.